So a very good evening, everyone. I, Ritik Velhan from Team CosmicShala, welcome you all to today's webinar on Search for Life in the Universe. I welcome our esteemed guest, Dr. Mila Mitra, to CosmicShala. Dr. Mitra is the co-founder and academic head of an innovative education company, STEM in Space, that aims to foster interest in STEM education through the exciting domain of space. She completed her bachelor's in science from St. Stephen's College in New Delhi and her PhD in astronomy from Rice University, Houston. She is an astrophysicist who has worked for more than 20 years at NASA on various satellite missions. She is fortunate to have had the experience of working on the Cosmic Background Explorer project while at NASA, which went on to win the Nobel Prize in Physics in 2008. She is an active science communicator. She has been the national coordinator for prominent international astronomy programs such as the All India Asteroid Search Campaign, Asteroid Day, and Global Astronomy Month. She has conducted many mass public outreach events such as solar eclipse observations. She has represented space events on news media and writes a regular astronomy column in Hindustan Times. A proposal written by her called Sky on a Bike won International Astronomical Union funding. She has been an invited speaker at several international conferences such as Global Hands-on Universe and recently at the first Aeronautics Conference in Brazil. While at STEM in Space, she has designed innovative STEM workshops and summer camps, including a Chandrayaan-2 workshop. The organization has been awarded Giant Moon and Mars Map from Buzz Aldrin Foundation for their education efforts. So, without any further ado, let's unveil the secrets of the universe with Dr. Mitra. I welcome Dr. Mitra to deliver her talk on Search for Life in the Universe.
Thank you. Welcome, everyone. And in CosmicShala, I thank you for inviting me today. And it gives me a great opportunity to interact with students and all other astronomy enthusiasts. So I see a lot of people here today, and I think you're all at different levels. Some of you school students, some college students. So it's going to be interesting for me to pick a level that everybody will enjoy. So don't worry about it if you find things too simple, or maybe you find some slides a bit too technical, because I'm trying to keep everyone happy. So with that, I'm going to start off. So I'm glad to see so many of you here today taking time out on a Sunday afternoon to find out more about our universe. And I've been seeing CosmicShala sharing different presentations. So, it's a very good effort to keep students and astronomers, amateur astronomers interested in these topics. So today I'm going to talk about search for life in the universe. It's a very vast topic, and I think it interests a lot of us, but obviously I'll be able to cover only some certain aspects of it. And I hope that gets you interested enough that you go and search more and try to find out more answers. Or maybe you try to follow the news on what's happening in this domain more. So as he's introduced me, I'm currently co-founder and head of academics, especially at STEM in Space. And we do workshops and space clubs in different schools, and also for any student who would like to join us. When we say search for life, there's so many movies that talk about life in the universe, or life that we encounter, right? All the way from E.T., one of the most famous ones, of course, Jadoo, Close Encounters, Wall-E. They make them cute. Some of them make them dangerous. But what is alien life really like? How will we know it when we see it? That's a very complex question, because there is no universally accepted definition of life. Because can we say that we will know life if it looks like us with two legs, a life that breathes oxygen? Will it be a green person, green man, little green man? Will it have an antenna on its forehead? All of this is unknown. So that's a tough starting point because it's unknown. So what we need to do is identify some traits or some parameters that we say, okay, we find that these indicate life, and we need to look for these telltale signs of life. So we only know life from what we have here on Earth. And we know that's intelligent life because it can communicate. So astrobiology is multidisciplinary. And for any of you who are school students or even college students, a lot of the way science is developing now, it is multidisciplinary. So, for example, astrobiology combines physics, chemistry, biology, planetary science, of course, satellite and rockets, and geography. So don't worry about it. If you're doing your BSc in one subject, you can still move on to very interesting fields of astronomy or space sciences. Okay, so astrobiology studies what is life, how did it start here on Earth? Because of course, again, Earth is our only clue of life. We don't really know it anywhere else. So that is the standard of reference that we use. So that brings us to, is Earth special? Why do we have life on Earth and why don't we know about it anywhere else? And finally, astrobiology studies, is there life in our solar system? And is there life outside our solar system? So I'm going to start off with Drake's equation. And this is the most technical slide on my presentation, so don't be scared of it. Okay, so all you need to know is Francis Drake started the concept of search for life. He's one of the main founders of SETI, Search for Extraterrestrial Intelligence. Now he formulated this equation, which looks very, it has a lot of parameters. So I'm going to start telling how do you determine N, which is the number of technologically advanced civilizations in our Milky Way galaxy. And he started off, this was many years back that he came up with this equation. So he said it is a function of the first parameter, which is rate of formation of stars. Every parameter to the right connects to the one on the left. So the first parameter is rate of formation of stars. The next one, FP, is the fraction of those stars that have planetary systems, because not all stars have planetary systems. Some of them might just be a star on its own. Okay, so the third term, NE, is if the stars have planetary systems, then which of those planets could have an environment suitable for life? And so on. You go to the right. But right-hand side, the last two parameters are fraction of civilizations that develop a technology that releases detectable signs, and the length for which such civilizations release these signals. So if you look on the top, there's a line. On the left-hand side, those things like rate of formations of stars, these can be studied. They're somewhat certain. But to the right-hand side, like, do technologies, can they release detectable signs? Do they have the technology? That these things become very uncertain. So Drake has this equation and scientists are trying to solve each of these parameters. But this is quite uncertain because what happens if there's microbial life? They won't have any technology, but they are there. So this is an equation that has been really governing the search for life, or trying to model, are there planets that could have life? And if so, are they habitable? And so on. Okay, so that is Drake's equation. So let's come back now to Earth, because the only thing we know about is, now we know a lot more, I'll come to it, but we are still basing everything on how did our Earth form and how did our solar system form. So let me take you back to when the solar system formed. I hope some of you are astronomy students. I think a lot of you are, because because the name CosmicShala would attract you if you're interested in this. So some of you might know this. Okay, so the universe was one big interstellar cloud of gas and dust. Eventually, there was a shock wave. Shock wave means how it was hit by something like a supernova, and it started forming a clump. Okay, so you'd imagine a big cloud of gas and it's hit by a wave, and it's part of it clumps up, just a small part of it clumps up. And that is the start of our solar system. And where it clumps up in the center, some of the clumps become very hot, and they start doing nucleosynthesis, or what is called nuclear fusion, whereby two hydrogen atoms create a helium atom, and this is what is nuclear fusion. And based on that is what powers the sun. Did you know that? Our sun is so powerful, it's got so much light and heat, but it's powered by something like that. Not only our sun, all suns are powered by that. Of course, all stars are in different parts of their life cycle. Okay, so this is the way the sun formed. The clump at the center uh, got a lot of material together, it became hot, and it started nuclear fusion. And it used up almost 95% or more of the material that had been in that particular cloud. Okay, so this is how it looked in the beginning. And because the sun was so hot and it had so much gravity, so it's only the rocky material that came closer to the sun, and the gassy material started going outwards. So these are the rocky material themselves clumped together and formed the first planets, which are Mercury, Venus, Earth, and Mars. And these are terrestrial planets. The ones beyond that, they are gaseous planets, because the gassy material all went outside. So that's how the terrestrial planets and the gassy material formed. And the little chunks that were nowhere, those formed the asteroids and the comets. So this is how our solar system evolved and how it looks like now. Okay, so here I have a detailed description, but I've kind of walked you through that. Okay, so what about the beginning of Earth? Earth now is so hospitable. It's got oceans, it's got mountains and trees. It gets warm at times, but it is cool also. That's what makes it habitable. But in the beginning, it was all very uninhabitable. It was very hot. There were lightning flashes. There were asteroid hits. Most of the atmosphere was nitrogen and carbon based, not oxygen based at that time. So this is how our Earth was in the beginning, but it slowly settled down. The water vapor started, as it settled down and the temperatures got a little cooler, the water vapor became water, and that's how oceans formed. And as you know, oceans and water contributed a lot to the formation of life. So in the beginning, basically, our Earth was a hot soup of such gases, and then the water formed. So here's an interesting experiment. Okay, so let me come back to this. And this is how life started forming. Because when there was water, then some of these elements were able to combine and create microbial organisms. So it is suspected that they were formed in the water, first of all. And such microbes were found as fossils pretty early on. So life started on Earth as microbes pretty soon after the Earth was actually formed. So there was in 1952 there was an experiment done by Miller, who wanted to play with this concept. So what he did was he created a closed system where he took the chemicals that were present in early Earth, which, as I told you, was boiling water because it was lava and hot water. And at that time, it was ammonia and methane were the gases present. And then he subjected them to this whole system to electrical shocks, because that's what, there was lightning. So the electrical shocks were supposed to simulate lightning. And what did he find? He actually found that the color of this system changed into a reddish color. And on analysis, they found two kinds of amino acids. And for any of you who remember your biology, and some of you might be biologists, amino acids are the building blocks of life and create protein. So Miller actually showed that an early Earth, the way the atmosphere and the environment was thought of at that time, could actually have led to life. Okay, so the first organisms found were microorganisms, and it started single-celled organisms, and of course these evolved, and life evolved. I'm not talking about evolution because that's a large topic of its own. Again, life evolved from water to mammals, water to reptiles to mammals. And then, of course, came humankind. And I hope you get the joke there. Yes, mankind evolved from apes, but the way, especially we are going in our lockdown, we are going to go back to crouching and not standing straight because we are back to the internet all the time, right? So anyway, humans were the first intelligent species. Okay, so this is called the tree of life. It shows you when different things evolved. Okay, now, the reason I'm talking about all this is because to search for life outside or outside our Earth, we need to know what is life, how is it defined on Earth, and why is there life on Earth? Why Earth? Why did we win the lottery? Okay, so what is life? You know what is life? It's a term to define physical entities that have certain biological activities. So what are the characteristics? There are several characteristics. I'll just talk about a few. Life is made up of cells, growth and development. So all life demonstrates growth and development. They contain DNA. They reproduce, they require energy, and they respond to stimulus. So why is our Earth special? Why did life develop there? So that brings us to what are the requirements for life? Earth has these conditions that fulfill the requirements: water, atmosphere, source of energy, and Goldilocks zone. Okay, so as you know, Earth is covered in about 70% water, and all the life forms are based on liquid water. Many of our bodies have water in them, and as I said, it's suspected that life started in water. Atmosphere, why is it so essential? Because it shields us from harmful radiations of the sun. Also shields us from also protects our atmosphere. Like oxygen and nitrogen are essential to how we breathe and photosynthesis. Okay, so the sun is a source of energy to us, and it gives us energy for all life, for plants, animals, humans. It creates a source of energy. Now, what is the Goldilocks zone? I don't know if you remember the story of Goldilocks that we read when we were small kids. So Goldilocks was a little girl who went into the forest, and she happened to go into a cottage that was lived in by three bears: a father bear, a mother bear, and a baby bear. So they had gone out when she went into the house, and she found some soups, some bowls with soups, and one of them was too hot, one of them was too cold, one of them was just right. And that's the story. She goes through everything in the house, and they're all too big, too small, and just right. So like that, there is a habitable zone around the sun. And if you're too close to the sun, then it's too hot. So Mercury and Venus, as you might know, are in an area that makes them too hot. So Then there's an area which is just right for habitation and for supporting water. And beyond that, again, it's too cold. So this is called the habitable zone or the Goldilocks zone. And not only our sun, but all suns or all stars have a habitable zone. And the habitable zone is not at the same distance for every sun or every star. It depends on how big the sun is and at what point of its life cycle it is. So basically based on how hot it is, the habitable zone might be further out or further in. And so this is the key point. To find habitable planets, you have to find planets that are in habitable zones, because we want to find planets that can support the presence of water. Okay, so what does life need to survive? Water. It needs a stable environment, needs an atmosphere, needs a source of energy. And on Earth, it's not only the sun, but it's all a source of energy. It's a cycle, because food is produced, there are nutrients in the soil, there's heat from underwater volcanoes. So there are different sources of energy that different animals and plants take up. So all these are important. And when we look for life in other planets, one of the key things scientists look for is water in different forms. It could be ice water, it could be water vapor, it could be liquid water. But basically, we feel that if there is water, there is a chance of life. And atmosphere, of course, we look for a habitable zone also, so that the environment and temperature is suitable. Now, I discussed so much about life and what they need, but there's an exception. The exceptions are called, there are some creatures that are microorganisms. They're called extremophiles. You know the word extreme, right? Extreme means maximum of something. So there are some creatures, microorganisms, that have been found to survive under very harsh conditions, like they survive in lava, they survive in Antarctic ice, they survive in, where in radiation zones. So that means that there are some creatures that can survive in extreme conditions. And this helps scientists or astrobiologists actually, they test out what are called analog situations. So for example, if you find a creature that can withstand heavy, very high temperatures, then scientists can test with a condition like Venus actually work, which is very hot. Will such creatures be able to survive? So that is a facet of astrobiology that's ongoing. I'll just introduce one extremophile to you. It's called a tardigrade. These look very cute to me. They're called water bears. So tardigrades can survive all kinds of extreme conditions. They can go without food or water. They can live in very cold as well as very boiling temperatures. They can be found in the deepest of oceans trenches. So scientists actually think of taking tardigrades, and tardigrades were in fact taken to the moon. And there was an Israeli mission that crashed, and tardigrades were in that. So by now there might be tardigrades on the moon. But yes, I just introduced this topic because there are some creatures who can survive in different kinds of conditions. So they contribute different knowledge to us. So coming back to, I told you in the beginning that we look for life. There are three things we do. The first one is we study life on Earth to determine what it needs, what defines life, and so on. Then we look for life in our solar system, and we say where all in our solar system can there be life. And finally, we look outside our solar system and look for other places outside our solar system that can have life. These are different research topics. So I already talked to you about life on Earth. Now let's answer, could there could there be life in other places in the solar system? And for this, we look for a habitable zone near Earth. I mean, only Earth is in the habitable zone. Mars and Venus are pretty close, but none of the other planets are in the habitable zone at all. Of course, for outside our solar system, there would be other stars with habitable zones. So mainly we look for water. So planetary habitability, NASA has defined these criteria: energy source, water, conditions favorable for organic molecules, and so on. But mostly in the solar system, we look for water. So there are different kinds of searches going on, ground-based searches. We look in the solar system and outside. So there are different missions ongoing. I'm going to talk briefly about some of these missions. So ground-based are mostly so far, radio telescopes, radio wave telescopes have been looking for life. SETI is the search for extraterrestrial intelligence. So radio telescopes are large arrays. And why radio telescopes? You can't see radio waves with your eyes, but they can penetrate the atmosphere, the dust and gas, and so radios. It's thought that radio waves might be a good way of communication. Okay, so in our solar system, there are some places that are thought to be potential, very little potential, but yes, there are. So let's start from the beginning. Mercury and Venus, maybe not, but recently, as some of you know, Venus has a thick cloud layer, and in the cloud there have been signs of phosphine, which is a chemical that is sometimes produced by microbes. So Venus is a target, and there will be missions to Venus in the next 10 years, including our own ISRO's Shukrayaan will be going in about 2026. So yes, Venus has a slight potential, but it may be very hard for life to persist there. Coming to Mars, it's thought that earlier life might have persisted because there are signs that there were water. Even now, Mars has been found to have ice caps, polar ice caps in the South Pole. And that's where Mangalyaan was trying to reach to explore more there. So there will be missions that will go to the polar ice caps and study further. So Mars has some potential. And of course, we are also exploring Mars as a possible location for space colonization. So, there are many missions that have gone to Mars. There are rovers that are studying Mars right now. And some of these rovers will be digging in further and creating samples. Okay, venturing a bit further out to Jupiter. Jupiter has a moon called Europa, and it has been found to have it is thought that there is an ocean below the moon's icy surface that is shielded from Jupiter's radiation. Okay, so Europa is a potential target. Now venturing out a bit more to Saturn. There are two moons of Saturn. If you look up, that's Enceladus. Enceladus actually has volcano-like clouds that are spewing out. And these have been found by the Cassini mission. And again, these could indicate water below the moon's surface. And Titan, as you know, Titan is a very well-known moon of Saturn. And Titan is thought to have lakes of methane and ethane. And methane is a telltale indicator of life. So in our solar system, these are the planets where scientists are focusing, not just planets, but moons, where scientists are focusing on looking for life. Okay, so I just talked briefly about these already. Yes, Mars is going to be one of our prime targets of exploration, Titan. Okay, so now let's go out beyond our solar system. So beyond our solar system, there's been a lot of news about it. You might have heard about exoplanets. Exoplanets, the word comes from extrasolar planet, means it's a planet outside the solar system. So the first possible evidence of an exoplanet was long back, but it was not recognized as such. So exoplanets are very different. So what they have contributed already in knowledge to us that they are not necessarily like our solar system. They have different kinds of rules, different kind of ways they form. So let's watch a brief video. And I hope you can hear the sound. Okay.
You're probably familiar with the major types of planets in our solar system. You know, there are some smaller, rocky planets and some giant gas planets. The rocky, or terrestrial ones, are closer to our star, the Sun, where it's much warmer, while the giant gas planets are farther out in the cold. But what about other planet systems we're finding out there among the stars? For the most part, they don't look a whole lot like ours. Turns out, there doesn't seem to be a typical arrangement for planetary systems. Yep, all planetary systems might be weird. Most other systems of planets are certainly arranged differently. Sure, there are lots of planets out there the size of Jupiter and Neptune and Earth, but their Jupiters and Neptunes can be way closer to their stars than ours. Some as close or closer than the orbit of Mercury. So scientists who study these exoplanets, planets outside our solar system, find themselves using terms like hot Jupiters and warm Neptunes. Plus, there's a whole range of exoplanet sizes, from much smaller than Earth to even bigger than Jupiter. To help describe what weight class each of these planets belongs to, we often refer back to the different planet types in our solar system, using terms like mini-Neptunes and super-Earths, or super-terrestrials. We're constantly learning more about exoplanets, and our ideas about them are changing as we go. Ideas about how these different planet types relate to each other, and what their variety can teach us about our own weird little solar system.
Okay, so exoplanets, like I said, are planets outside our solar system. And there are several missions studying these. And when I say studying them, do realize that exoplanets are very hard to study. They're very, very far away. You cannot just survey it by looking at it. You have to survey them in special ways. Okay, so some of the famous missions, of course, Hubble, you know. Hubble was followed by Spitzer. In the next couple of slides, I'm going to talk about Kepler and Kepler's contributions and TESS. And next, we are going to have James Webb Space Telescope that is going to fly later this year itself. So all these missions have contributed a lot of knowledge to study of exoplanets. Okay, so the Kepler mission was launched in 2009, and it actually took data for about 10 years. And it's search for extrasolar planets. And it observed more than 500,000 stars, and it found close to 3,000 exoplanets. Okay, so like I said, exoplanets, or you cannot really very easily identify exoplanets visually. It's not like observing a sun close to us, or a planet, or a nebula close to us. So there's a special way. There are 2 or 3 special ways of finding them. One of them is called the transit method. If you look on the right-hand side, a transit method is the same concept as an eclipse almost, which means that when a planet comes in front of a star, again, look at the right-hand side where it says transit on top. If the planet comes in front of a star, the star's brightness for a brief moment decreases. So that's what these missions do. They keep on observing the brightness of different stars, and over time, they scan it and survey it over time. And later, if a dip is found, that dip might indicate that something passed in front of it. Okay, so there's also a radial velocity method in the left, and I'm not going to talk about that right now. Most of these missions are using the transit method, which means looking for a dip in the brightness of a star. So Kepler mission looked very far out and in focused rays, focused directions, and using this method, it observed 500,000 stars and found almost 3,000 planets. Okay, so the top science is they found a lot of planets. They found that small planets the size of our Earth are quite common, and planets are diverse. means they may not look the same as us. Just like the video, there might be a planet closer to that sun, but it might be cold. Okay, so Kepler mission was followed by TESS, which is the Transiting Exoplanet Survey Satellite, and this is ongoing. It launched in 2018. This has a different strategy. It's poised in an orbit that will let it survey a much broader, wider area, but it will observe closer to our solar system and not so far out. This has the advantage that if it finds something, then follow-ons like James Webb Space Telescope might be able to study those specific things. Because they're closer, it will be easier to do follow-on studies. Okay, so again, TESS has found many candidate planets. And what I mean by candidate planets are they try to find ones that are habitable in terms of temperature or distance from its star. And so it has, but it's also found very strange stars. This is one star it has found that's almost a solar mass, but and it has found a possibly habitable planet around it. Okay, so you can see this graph. The dots in blue, dark blue, are the missions before Kepler, and you can see yellow dots are the ones exoplanet discoveries that were contributed by Kepler. There have been other missions sent by us long back that have now reached interstellar space. This includes the Pioneer missions and the Voyager missions, and these have contributed information on Jupiter, Saturn, Neptune, and now they have reached interstellar space. Okay, so now with this knowledge that there are so many exoplanets and possible habitable planets outside, the Drake equation was modified. So if you look at the blue words below, now the Drake equation has been simplified to just a function of number of habitable planets in a given volume times the likelihood of a technological species arising in one of these planets. So basically our study should keep on looking for habitable planets and trying to identify telltale locations of life in these planets. So these are contributed by Kepler and TESS. We have so many possibly habitable exoplanets, and missions like JWST will be targeting these ones more. Okay, so again, is there anybody out there? And with that, I'll end my talk, and I can take a few questions. And I know CosmicShala has a very exciting quiz for you. Okay, so let's take some questions. And you can reach me. I forgot to write that for my email ID. It's Mila, M-I-L-A, @stemandspace.com. And STEM and Space again is our website, so you can take a look. So I hope you, I hope you all got a good understanding of just a lot of topics that relate to looking for life in the universe. Yeah, thank you, Manash, for sharing my email ID. And yeah, so I'll take a few questions.
Thank you so much, ma'am, for the wonderful and fascinating talk. It was indeed an enlightening session, imparting much needed knowledge to everyone, which is clearly visible by the questions that have been pouring in the chat box. It gave a detailed insight into a new world for many of us, I'm sure. So before starting with the questions, I would like to briefly tell everyone that we have a quiz prepared for you on the Quizzes app. So if you haven't installed the app, go to the Play Store and install the app right now, and we'll give you the code on the WhatsApp group itself, and we'll write it here as well for people who are not there in the WhatsApp group. So to begin the Q&A session, I would like to first address those questions which we have received at the time of registration in the form. So there were a couple of questions that I felt are related to the talk, to ma'am's talk. So ma'am, the first question that was asked by Apurva is that what have we found in our search for extraterrestrial life? So I know you have covered a little bit of base here, but if you could be a little specific as to what all has been covered.
Yeah. So we haven't really found, we haven't found signs of any intelligent life, and that itself is an answer. Because if we haven't found it so far, with the kind of technology we are using, there is a good chance that there isn't intelligent life in our solar system at least. And or because even we've been using radio waves and different kinds of wavelengths, so it could be that either we are not using the right technology. But yes, there is no intelligent life we have found, but we have found possibilities of uh, past life, or microbial life in some of the planets even in our solar system.
So another question that was asked by Raghav was that, can you suggest some books for learning astrobiology? So I think that goes for everyone if people are interested for learning astrobiology.
So, NASA is really pushing astrobiology. And if you go to the NASA site and look for astrobiology, they have a lot of material there. So I'd recommend that you go there. And they have, different tabs for these kind of missions I'm talking about, and about search for life and ground-based search for life. So yes, go to the NASA astrobiology site.
Okay, so now I'm going to unmute the participants one by one so that they can ask their questions directly to you. So I'll unmute Simrandeep first. So I've seen that this person has been active in the chat box, and Simrandeep, be ready, be prepared with your question or questions. I'm going to unmute you now. So now Simrandeep, you can unmute yourself.
Thank you, sir, for unmuting me. Good afternoon, ma'am. Ma'am, I wanted to ask, what if we found futuristic humans on another planet? Would it still be considered as extraterrestrial life, or what would we say to it?
Yeah, so you have several points tied in, like futuristic, not humans, but futuristic, maybe aliens. Yes, they would be considered extraterrestrial life, and we would like it if they have the technology to to communicate. Maybe they're more futuristic than us, but yes, they would be considered extraterrestrial, because the word extraterrestrial means outside our territory, which is Earth.
And ma'am, can I ask one more question, or is it limited to one question?
Sure, you can ask. You can ask your carbon-based question. I'm seeing this in the chat box.
Yes, ma'am. I had the question that, ma'am, is there any possibility that life can be other than carbon-based molecules?
Yeah, that's what I said, that the problem is that you're right, it can be, but our scientists have to go with the assumption of life as we find it here. And that is why they feel carbon-based is is one of the telltale signs that they do look for. But yes, it can be otherwise also.
So now,
as you can see, there are many unknowns. So we have to go with some of the known parameters. Yeah, go ahead.
Yeah, so now I will unmute Meghna Vyas. So Meghna, be prepared with your question and you can ask it to ma'am. So now you can unmute yourself.
Good evening, ma'am and sir. This is Meghna from Rajasthan. I had the question that the definition of life that we discussed, that they should have cells and DNAs and all those. So that is for the life that is existing here on Earth, right? Do we have any, can we use spectroscopy to determine the presence of life? Like, because elements will be same, like usually like same elements were created, so elements will be same, and using the spectroscopy we can guess if the life is existing.
Yeah, so it's a good point, but usually spectroscopy, you're conceptually correct, because spectroscopy is used, but spectroscopy is usually used, you have to have, especially when you're trying to find the composition from outside Earth, something that you can't have close by, then it is spectroscopy of light. So it is, so it is spectroscopy of what light is emitted. So yes, but you are right in terms of you can do the spectroscopy of the atmosphere, and that is how one of the ways in which phosphine was found. So you can do spectroscopy of the atmosphere of different places and find what kind of content there is. Because if a human or an alien is releasing methane, for example, it should be able
Exactly,
to
that
found
was
spectroscopically. Yeah. So yes, you can find it spectroscopically in the atmosphere, or
so.
if we actually reach somewhere, then even in the soil or the ground.
Is there any specific definition in spectroscopy for life? Like, can we somehow, I don't know how to ask this, but can we somehow detect the presence of life, any specific kind of movement of the elements that show that there is presence of life?
So, see, not yet like that, but yes, there are certain elements we are looking for, like carbon dioxide, methane, and all of these are thought to be signs of photosynthesis or signs of life. But
Okay.
otherwise, spectroscopy is even used for, like I just talked about, exoplanets. And I told you one of the methods to find exoplanets is to look at transit, like when the star in front of them changes in brightness. But another way to look at them is spectroscopy. And through that, there's something called red shift and blue shift. So if the star is, so basically the spectrum, if it changes, it indicates that there is a moving planet around the star. So this is how another way of using spectroscopy to find exoplanets. So yes, thanks for asking these questions. Spectroscopy is used a lot in such kind of research. Yes.
So I will unmute Sneha Munshi next, and she can ask the question. So Sneha, be prepared with your question. Now you can unmute yourself.
Ma'am, I had a doubt that whether is there a possibility that the alien life which we are in search of, it may or may not be, it may or may not be made up of normal matter, rather it may be made up of antimatter or some type of other matter which humans have not discovered yet, and it might be even invisible.
Yeah, that's very possible. Not just antimatter, but radiation, for example, or different types of radiation. But like I said in the beginning, this topic is very complicated because you don't know what you're looking for. So that's why scientists start with not just uh, telltale signs of what life here is on Earth, but they do look for radiation variations, and that's what a lot of these radio wave telescopes do. They look for signals. So so if signals are changing or coming from somewhere, so there is a constant survey for those kind of things also. So hopefully, that's all we can do. We cannot have the research to look into all possible kinds of life structures. But yes, you're right. That's, but that's where other interdisciplinary studies, like CERN is looking at elementary particles and how they are formed. So interdisciplinary studies will add up. So, so if there are elementary particles or radiation, they might be found in other studies that indicate that there is something that is strange out there.
Good evening, ma'am. It was amazing to hear you. My question is that you talked about the transit process, right? So in the transit process, you also talked about how there's a deflection in the brightness that comes out from the star.
Right.
So how can we get to know about that brightness, that there's even that small sort of deflection, if there is some?
Right. And I'm going to tell you about this, but for any of you who are interested, there is actually, okay, so let me tell you about this first. So how it works is, it's like a survey. So something like Kepler or TESS, they survey a part of the sky for a long time. Otherwise, they rotate back and come back to it. So, so there is a star that might be surveyed for over many months. And that's when, and they can't tell it right away. So if the brightness of star is coming out to be a certain value, suddenly at a 3-month level, if you find there's a dip in the brightness, that's what could indicate that something passed in front of that star. So it is a survey, and you may not know the answer right away. And there are scientists who analyze that data later on and look for it. And if any of you are interested in looking at that, there is a citizen science project. I don't know if any of you have done citizen science, but there is a site called Zooniverse, and there is data from, and I just put in the chat box, you can go to the Zooniverse website, and there's many projects there that you can contribute to. It's very easy. And there's a project called TESS there, and TESS data is there. Even citizen scientists can go and look for transits, like where the brightness dips. You can look at a lot of stars and try to identify that. Okay, so I hope that answers your question.
Thank you so much, ma'am.
Thanks.
So I have been receiving a lot of requests for unmuting their mics. But first, I would like to ask, ma'am, how many questions can you take? How many more questions?
Yeah, I'll take a couple more, and then I'll share my, my email ID again, so that you can feel free to chat with me.
Sure, ma'am. So I will unmute Neil Raval first, and then Chahat Grover, because constantly in the chat box they have been
right.
requesting.
Right.
So yeah, I will unmute Neil Raval.
Good evening, ma'am. Ma'am, my question is that, as we know, Hubble is an optical telescope. So whenever it clicks pictures of exoplanets, it will get the light which is reflected from the exoplanet since a very long time, right?
Right.
Then we will get the images of that time, right? Then is it there possible that there may be an intelligent life surviving at present?
So, yeah, so Hubble, the function of Hubble is not only for looking for exoplanets. Kepler and TESS are more meant for that. And JWST, which is going to go up in November, James Webb Space Telescope, is also going to be looking for exoplanets. Hubble was more doing, imaging of different celestial objects. So yes, it is. It doesn't do a survey. So you're right in terms of it takes a photographic capture of celestial objects to show the details in that object. So yes, it may or may not find even exoplanets because it's not doing a continuous survey of the sky and covering different areas. It has different celestial objects that is looking at. So Hubble did contribute to this study, but that is not its purpose, actually.
So I will unmute Chahat now. And maybe this is the last question, since I have been prepared with the questions. So now you can unmute yourself.
Hello, ma'am. Good evening.
Good evening.
Yes, ma'am. So I had to ask that, have we got any proof till now that there was life in Mars?
We have not, unfortunately, because as you know, we have been really trying because we have sent several missions and we have sent rovers that are trying to actually take samples of the soil. So what they're trying to do is they try to take samples in volcanic areas and wherever there might be some channels that could have had water. So they try to look at specific. So the thing is, all of you are, asking the right questions. The thing is that every year, every mission we send, we are getting additional information. So it's not just a question of have we found it or not. The thing is, what we found is there is no obvious sign of life now. And that itself is a big achievement because that means we were able to get rovers onto the Mars surface that were able to give us many more answers. We also know that there are volcanoes there. There is some sign of past water, not current water, but past water. And there are also polar ice caps. And why polar? Because in the poles, they're more shadowed, so they retain the coldness, so they can stay in the ice cap sense. So all this information we've gathered from different missions. And, it's only a question of we move forward and see, was there a signs of past life? And if there was, why did that life go away? Or is there still a sign of microbial life? So the good point is that there are some promising facts about Mars, but yes, we have not found any conclusive proof of any life anywhere in the solar system yet.
Okay, ma'am. So I also had a doubt that wanted to ask that how far have we gone in space till now?
So we have gone to the, like I showed you in the slide, there are two missions called Pioneer and Voyager that have actually crossed, and all of these missions are flyby missions. So they don't land, they don't, or there are different types of missions. There are flybys that go past, there are orbiters that catch on to the orbit of a certain planet, and like our Mangalyaan, and also there are some that land. So these are the flyby missions that are still going, and they have reached the end of what is called interstellar space, so end of our solar system. And there are different satellites called deep space network that are still able to send the signals back to us. So yes, they have gone to the end of the solar system.
Ma'am, so it is a request for just a couple more questions if you can squeeze in.
Okay. Yeah, sure.
Yeah, because these guys are they are on fire. Actually.
No, that's great that they're interested in this topic.
Yeah, because if you check the chat box, they are asking again and again, they're requesting again and again. So I'll unmute user. The name is user. I don't know who exactly this person is. So please ask your question.
Hello, sir. I'm audible.
Yeah, you're on.
Yes.
Please ask your question.
मेरा नाम तेजस है, ये मेरे पीसी से मैं जुड़ा हूँ, वहाँ पे थोड़ी सी प्रॉब्लम है, इसकी वजह से मैं नाम नहीं डाल पाया हूँ, सॉरी उसके लिए। और दूसरी एक बात है कि ये अभी आप जो मैम है वो क्या नासा के अंदर स्टीम के अंदर काम करती है, जिसके जो नासा के कुछ वेबिनार होते हैं उसके अंदर वो हेड है उनकी, तो उनसे मुझे पूछना था कि अगर वो पॉसिबल हो तो उसकी जानकारी हमें मिल सकती है, रिकॉर्डिंग मिल सकती है, तो यहाँ पे जितने भी जो स्कूल स्टूडेंट है कॉलेज के अंदर जो जाते हैं उनको ये हेल्प हो सकती है। और दूसरा मेरा क्वेश्चन था कि नासा के कुछ प्रोजेक्ट होते हैं या इंटर्नशिप जैसा कुछ होता है, वो यूएस के नागरिक के लिए होते हैं, क्या भारत के लोग भी हिस्सा ले सकते हैं? ऐसा कोई कॉन्टेस्ट ऐसा कुछ हो सकता है तो प्लीज उसके बारे में बताइए। मुझे सिर्फ इतना ही जानना था, जिससे ज्यादा से ज्यादा लोगों को इसके अंदर आने का मौका मिल सके और ज्यादा से ज्यादा लोग इसमें ज्वाइन हो सके।
मैम विल आंसर।
ओके, तो अभी मैं नासा में काम नहीं करती, प्लीज एक्सक्यूज माय हिंदी, बट ओके, मैं पहले काम करती थी वहां पे और तब मैं यूएसए में ही थी। एंड जो नासा में काम करते हैं वहां पे रिक्वायरमेंट है कि यूएस सिटीजनशिप चाहिए, नहीं तो ग्रीन कार्ड चाहिए। आप कॉन्ट्रैक्टर्स के लिए, फॉर एनीबडी हु इज इंटरेस्टेड, आई एम गिविंग यू दिस इंफॉर्मेशन बिकॉज अ लॉट ऑफ पीपल आस्क नासा में कैसे काम कर सकते हैं। So there are contractors there. For example, I started working with Northrop Grumman, which is an aerospace company. ये लोग लेते हैं जो नॉन सिटीजन्स है और उनको कोई प्रोजेक्ट में डाल देते हैं जो नासा में ही होता है, उससे आपको एक्सपोर्ट डायरेक्टली एंट्री मिल जाता है नासा में। तो ऐसे, लेकिन इट्स क्वाइट हार्ड टू गेट इन। आपको यहाँ से अप्लाई करना बहुत मुश्किल है, आपको यूएसए से ही अप्लाई करना पड़ेगा। जैसे मैंने वहां से ही पीएचडी किया था तो मुझे वहां से ही एक्सेस मिल गया था, क्योंकि वहां पे जो जॉब्स एडवर्टाइज करते हैं फिर आपके एक्सपीरियंस से ले सकते हैं। सो somebody else is asking SpaceX में, SpaceX might be more possible because see, NASA is like the government. Even ISRO has the requirement that you have to be a citizen, क्योंकि वहाँ पे सिक्योरिटी क्लियरेंस का जरूरत होता है, वहाँ पे बहुत क्लासिफाइड काम होता है, तो उनका रिक्वायरमेंट होता है कि आप सिटीजन ही हो। लेकिन आप कॉन्ट्रैक्टर बन के आ सकते हो कोई एरोस्पेस कंपनी के थ्रू से जिनका रिलेशनशिप या कोई प्रोजेक्ट हो नासा के साथ, या स्पेसएक्स, वर्जिन गैलेक्टिक, इन सब में भी चांस आपको मिल सकता है। Even I know somebody, Indian citizen ही है, जिनको वर्जिन गैलेक्टिक में जॉब मिला है। तो आप with your engineering degrees आप अप्लाई कर सकते हो, but you have a better chance if you are already in the US जब आप अप्लाई कर रहे हो। तो yes, I'm not in NASA anymore, so I can't give the direct information. I'm just sharing my past experience जो मेरा था।
Yeah, so last question for the day. I'll unmute Gohar now, and I'll share ma'am's email ID in the WhatsApp group. So you can, all of you who still are requesting me to ask another question, you can ask these questions to ma'am directly on her email. So I'll unmute Gohar now.
Hello, thank you for giving me the chance. I want to ask, everyone was evolving right now and how universe made for. So lots of search on internet, I get the number 42 concept, but what exactly it is? Can you please elaborate once?
Can you just repeat the question? So I didn't hear it properly.
What is the concept of number 42?
I'm not sure where I used the number 42. I think I saw this in the chat also. I'm not sure where I used it.
Actually, I'm evolving and gathering some data about how space and how universe was created. So I get to know this concept. So I don't know what it is.
Okay, sorry, I haven't heard that number in connection to any of this. Sorry, I can't answer this particular question.
So anyway, it was a nice session. And now for the closing ceremony. So on behalf of the entire organizing team, I, Ritik, deem it a great honor and privilege to propose the vote of thanks on this occasion. First and foremost, we thank our esteemed guest, Dr. Mila Mitra, who, despite her busy schedule and commitments, agreed to grace this occasion and share her valuable knowledge and research work with us. We're also grateful to our organizing team who have worked hard to ensure smooth functioning of this event. And last but not the least, I thank all the distinguished participants present here for joining us today. We appreciate your cooperation and patience and hope you overlook the technical glitches encountered, if any. So thank you, everyone, and hope you have a wonderful journey with CosmicShala. And yeah, this is it. But please don't leave right now because I will give you the instructions for the quizzes app where the quiz will be held. So thank you again, ma'am, for this wonderful, wonderful presentation. And maybe we'll invite you again. Maybe we can have you again. We'll be distinguished enough to have you again here with CosmicShala.
Yeah, thank you all participants for being so interested and enthusiastic and asking so many, very good questions. And thank you, CosmicShala, for inviting me. It was really a pleasure.
You're welcome, ma'am. Thank you.
Thank you.